All right, so let's go back. So, as you see, since this is taped, I'm wearing proudly the colors of the institute I'm the director of. Maybe so that if they go online and they're jealous of me being on the beach, they see that I'm here working and carrying the flag. All right, so yesterday I introduced the history of this and introduced the models. So if you are lost, let me remind you again what the model is. So we have the cubic model and the spherical model. On the cubic model, the hard spin model, or the easing speed model, the configuration space is the vertices of the hypercube, and that's the first thing. And then the energy is given, or the Hamiltonian is given by this. The p-spin Hamiltonian is given by that, 1 over n to the p minus 1 over 2 sum of ji1 ip sigma I1 sigma ip. From I1 ip is 1 to n. And the general mixed spin model, Hamiltonian, is given by sum of beta p hnp of sigma from some p equal. Usually I don't include the case p equal 1, but Talleyrand, Panchenko, do include it. And here we assume that this series converge uniformly or converge well if this series is infinite. So typically you assume that the beta p's go to 0 fast, so maybe something like this. But you may as well think of, if you want, as a finite sum. And then the Gibbs measure is just given by exponential minus beta hn of sigma at temperature, inverse temperature beta, normalized by Zn, where Zn is the partition function, which is just the sum of these guys. All possible sigma, the 2 to the n configurations. And beta here is the inverse temperature. So we may or may not add here, maybe I could write it separately. We will also look at the case where you have possibly an external magnetic field where H is a real number. And so this would be that. All right. But you could forget H and think of H equals 0 if you want. So that's the, so let's put that in. Okay. So that's the measure, and of course what we want to understand is the behavior of the partition function and the behavior of the Gibbs measure. Remember that when you look at this guy here, that's one way to see it, the Hamiltonian, but the really intrinsic way to see the Hamiltonian is to say that it is Hn of sigma is simply is a Gaussian random function. Of course, here a random function is simply a random vector on sigma n, centered, and where the covariance, that's the important structure, the covariance of Hn at two different sites is given by n nu of the overlap of sigma and sigma prime, where the overlap is just the inner product normalized. So it's something which sits between -1 and 1. And where the function nu, which is the important parameter here, the true parameter of the model, is simply the sum of beta p square r to the p. Okay, so this function nu is the crucial, maybe I should keep it here, nu of r is the crucial parameter. It's just equivalent to the data of the beta p's. Gives you the mixture. All right, so and again, yesterday I stressed the following fact. This says that the covariance of the Hamiltonian is a function of the distance of the 2 points, because this is directly linked to the distance of the 2 points, right? So again, it says that the natural metric defined by the Gaussian vector is equivalent, is a function of the metric on the cube, okay? And it would be the same on the sphere. That's really probably the best way to introduce those models is just to look at this type of thing. This contains the whole information. So now we have this random function on the cube. We look at this random measure, right? This measure is random since Hn is random. And at this random number here, which is the free energy, and we want to understand them. All right, so as I said, this has been done by Parisi at the level of rigor that I described yesterday a long time ago. And since then, we are struggling to understand it completely. But there is one thing which is proved, and that's called the Parisi formula. It was a huge achievement. So Parisi formula, or maybe Parisi's formula, gives, in fact, the free energy. It gives the limit. It's not at all clear, maybe, that this limit exists, but it does. So when you look at this, so Zn is a number, but it's a random number. You compute the log of Zn, divide by n, take the mean, and take the limit when n goes to infinity. So 2 remarks here. We could also be interested in looking just at the variable 1 over n log of Zn. This is a random variable, and not the mean. But we are not losing much by taking the mean, because in fact there is concentration of this variable on its mean, right? So that's an important remark, is that and that may be the first remark. I won't come back to that. That's not very difficult. It's kind of now standard Gaussian concentration result concentrates on its mean. So we don't have any surprises to expect here. You know, sometimes it happens that you can compute the mean of the first moment of a random variable, but you don't know anything about the random variable because the second moment is huge or something like that. Here it's not the case. This concentrates on its mean. So that's the right object to study. Second remark, we could try, so this limit exists, and the Parisi formula gives this limit, right? And I will say what this is here. So that solved the first question. You remember yesterday I said in any statistical mechanics type of things, you have first to understand the free energy. So this gives the formula for the free energy. And of course, this expectation here means expectation in the disorder, expectation in the Gaussian function. All right, so before I describe this, because this right-hand side is really a mysterious object, and it will take time to even master what it says, let me say something else here. This is usually, in the physics literature, has been called the quenched limit. And this is very misleading, but why is that called quenched? In fact, it means you have the disorder, okay, and you fix the disorder, and you look at this variable. So here there is a mean, but if you know that it concentrates, essentially you're looking at the almost sure behavior of this quantity in the disorder. And this is quenched. Quenched means fixing the disorder. You could do something else, which is way simpler, and you could study this. Right? So this limit here, sometimes called the anneal limit, is in fact trivial to compute. Of course, there's a link between the two by Jensen's formula because the log is concave. And for those of you who don't remember in which order Jensen's function, do it. But this is, of course, a very easy computation, right? Because if you look at the expectation of this, right, the expectation, of course, commutes with the sum. Then you have to compute the expectation of that. And this is exponential minus beta, a Gaussian variable. So you're just computing the Laplace transform of a Gaussian variable. Not very hard, right? So that's a trivial computation. And of course, this limit is completely different from that, usually. But, so let me just for a moment say something. Before we go there, let me say how the Parisi formula came about and how the physicists tried this computation, the famous replica trick and all that. So at this point, fasten your seatbelt. Everything I'm saying here is, if it doesn't make sense, you have to just be in the company of every other mathematician in the last 30 years. So here it is. So that's a simple computation. Then the physicists thought the following. Okay, that's a simple computation, but we could do a little more than that. So I could compute when a is an integer here. Right? I could compute the moments of Zn. Why? This computation is easy to. Because look, if you take this, forget this h for the moment, take that, take the power 2 or 3 or 4 of this, what will you get? A sum of exponential, of products of those exponential. So you will have exponential minus beta, hn of sigma 1 plus hn of sigma 2, etc. This still will be Gaussian. Now, you can compute the variance of each of these guys because you know the covariance between h of sigma 1 and h of sigma 2. So you're back to the same computation, right? Laplace transform of a Gaussian. So you can do it. Right? You can compute that, and you can even compute this limit. It's not very hard. Exercise. Right? Okay, so you have a limit like this. So why would that be useful? Let's say you have this for any integer a. Exercise, you can compute that. Let's call, I don't know, this function phi of a, which is defined on the integers. Right? Now you use the following thing. This is the basis of the trick of the so-called replica trick. So why is that called a replica trick? So why is replica here? It's because when you compute the Zn of a, as I just said, you get, so let me write, I don't know, Zn of the n to the square, and take h equals 0. It's just sum over sigma 1 and sigma 2 of exponential minus beta hn of sigma 1 plus hn of sigma 2. Right? Simple. And you want to compute the expectation of that. So why is that called replica? It's because here you have fixed the disorder. You have the same disorder here and here. Right? You fix the same omega if you want. And in the same disorder, you're looking at two replicas of the system. Right? So you can do this computation for 2, 3, whatever. Let's imagine you can compute that. Then what do you do with that? How is that related to this? The idea is simply that if you take log of z, you can write, if you're a physicist, you write, and it's not absurd, that it's Zn minus the a minus 1 divided by a when a goes to 0. Right? Easy. Z to the a is e to the a log z. When a goes to 0, this is a log z plus 1 minus 1 divided by a, that's log z. Right? Okay, so if you want the expectation of log z, you may think, all right, so you could approximate it by the limit, or say that it is the limit when, hoping everything goes properly, when of 1 over n e to the z to the a minus 1 divided by, right? A, whatever. So once you know how this behaves, so let me write this, then you should obtain the behavior of the log. There's that. The problem, of course, is here you need to have A go to 0. Right? And we know the behavior of this guy when A is an integer. Right? So usually the next trick is of the following type, and it's not always absurd. It's, again, here you're looking at the distribution of Zn, and essentially you understand the behavior of its moments. Right? And from this you want to derive its law, essentially. That's what this thing is supposed to do here. So sometimes it works and sometimes it doesn't. So there is this, then the replicate trick consists in finding a way to extend the formula you get here for A integer to A real number. Right. This takes a lot of ingenuity. And once you've done that, this analytic continuation, if you want, from integers, you let A go to 0, and you hope that the limit will give you the right behavior. Okay. The problem is, so that was not done by Parisi. That was done before, as I said, by Sherrington and Kirkpatrick. But when they did that, in some sense, they realized that their analytic continuation was going to a limit that was meaningless. What Parisi did was propose one way to do it that in the end is right. Right? This route we can't really go. Of course, I didn't show you how you make this computation. The real idea of the computation is that this phi of A is obtained as the solution of a variational problem. Not hard to guess. So you have a variational problem, and what really Parisi does finally is not trying to extend the value of this phi of A to a non-integer. He looks at it as a variational problem, and he finds the minimizer of this variational problem, or maximizer, depending on how you look at it, and extend the variational problem itself and the definition of the minimizer. And this is where you have a problem, because in fact this variational problem here is on matrices of size A by A. When A is 17, that's okay. But when you want to try to understand what you're doing by looking at matrices of size A equal a half by a half, then you're really in trouble. Right? Nevertheless, he was totally right. Everything he did, so you have to make sense out of that. And this is the initial thing of Parisi. This is this thing that is still. So there are very nice. If you read this huge literature by Talleyrand, there are very nice things that Talleyrand says that, because he spent so many years on that. So at some point he says it's the belief of the author, meaning him, that trying to put this thing on the right footing is worthless now. It's maybe the only thing there is to the replica symmetry breaking scheme of Parisi is Parisi. And so in some sense he gives up on the idea of building that. Of course, not on the idea of proving the Parisi picture. All right, so let's forget this. We won't be doing that. And I don't want to go too far into that. So now what do you obtain here? So we will see that this limit here is equal to, so that's the Parisi formula, that's a theorem, to the minimum of a certain functional, which is usually denoted by a P for Parisi, but we have too many P's with probabilities, and I don't have as much calligraphic ability as tech, so I will denote this as par, like Parisi. That's the Parisi function. And it's a minimum of this Parisi function, which depends on all sorts of parameters. In fact, it depends on nu, it depends on beta, and on h, of course, if there is an h. So these are the parameters of the model. Beta is the inverse temperature, the external magnetic field. Nu is the structure of the covariance. It's minimum of, say, rho, and it's a minimum of a rho. And I will say what rho is. Rho is a probability measure on 0, 1. Okay? So that's the formula. Of course, I have to describe what this functional is. Of course, in fact, instead of describing rho as a probability measure, I could as well describe it as a distribution function, right? So instead of rho, I could consider, say, zeta of rho. Zeta is just the distribution function. So that is, and I could take the minimum on all zetas. So which means, so here is just a function from 0, 1, in fact, to 0, 1, which is right continuous, left limits, I mean, the usual thing, and non-decreasing. Okay, and of course, zeta of 1 is 1. Okay. So I could parameterize this, the rho by the distribution function, and that's what is usually done. Right, so let me describe this. In fact, the formula could be described, this object, let me call this object f, and so it's a function of beta, nu, and h, but let me just keep beta as I could put nu and h here. Okay? So this f is this. In fact, this f was initially described as, in a different way. It's described as a minimum of this Parisi functional, if you want, on rho which are purely atomic. Or if we want, it's also the infimum here, right? I didn't say that it's achieved yet. Infimum. Which is, of course, also the infimum of this Parisi functional, written as a function of zeta, where zeta is, in fact, a step function, a step distribution function. Okay? So initially, it has been described like this. So I will first describe this definition of this Parisi function on a step function. Then, of course, and in fact, most of the theory today is done with this. You don't really need to write it, to extend this Parisi functional to all possible distributions or all possible probability measures. But you can, right? It's not necessarily needed. You can simply look at it as an infimum over all discrete probability measures if you want. Nothing tells you that, of course, this infimum is achieved on such a discrete thing. Okay? If it is achieved on such a discrete thing, then we will say that there is a finite level of replica symmetry breaking. Okay? So what is this? So this object is really bizarre. So let's start with the definition. So I take an atomic measure with k atoms, which is the same thing, a discrete step function. So to describe a discrete step function or a discrete atomic measures, I need the positions of the atoms and the mass of the atoms, right? So such a zeta is described by the position. So let me call this Q0, Q1. These will be the positions of the atoms. Qk plus 1 equals 1. And then I need the position of the value of the atoms. So I have M0, M1, etc. So I will assume this. Because, no, this will not be the mass of the atom. This will be the values of zeta. The mass of the atom will be the differences. Okay? So if you want, zeta is the measure sum of, or rho It's the measure sum of ml minus ml minus 1, direct mass at QL. Okay? Right, and for such a thing, I define now the Parisi functional, which is, as you'll see, a bit bizarre. So, yeah, so for the sake of notation, I denote this to be 0 here to follow the. All right, so. I want to really not get bugged by the. So what did I choose here? Yeah, maybe k instead of k plus 1. I'm sorry. Just choose the last one. All right, so sorry for that. I should have put it on the front page. Okay. Oh, I'm sorry, I shift this. It's 0 here. K. And 0 here, and QK. Smaller than QK plus 1. All right, so that's my rho or my zeta, if you want. Zeta is, of course, the step function corresponding to that. Then I introduce the following. I introduce ZJs, which are independent random variables, Gaussian, centered, and with variance given by nu prime of q of j plus 1 minus nu prime of q of j. Okay, where nu is the parameter, the functional parameter of the model, this function here. And then I look at the following. I define this random variable, xk plus 1, I start by the n, as being log of cosine, hyperbole cosine, of the sum of the zj's from j equals 0 to k. Okay? That's the random variable. Okay? So this is, in fact, a function of this whole collection of z0, z1, zk, Gaussian random variable. And then I partially integrate it. So then I look at L, for L smaller than k plus 1, to be 1 over this ML. So for the moment in this definition here, or here, we don't have the mass of the atoms. We have the positions of the atoms only. Right? Now I put the mass of the atoms. It's 1 over ML log of expectation, let's say index L, of exponential of M L x L plus 1. This expectation here means expectation on the ZL plus 1 random variable. Okay? So take the time to understand what we have here. Forget there's this log cosine hyperbolic. That's not the important structure. Of course, this function is crucial, but you have a function here of k plus 1 random variables. Then what you do simply is to define xk, you integrate the last random variable out. So what you get is a function of the first k random variable. And then you integrate the next to last, etc. But you integrate them in this strange way. Right? You take the exponential of this, multiply by something, and then divide by something. If this m were 0, you would lose this nonlinearity. You would simply look at the expectation. But here I just assume all the m's not to be 0. Okay, so that's a strange object. And in the end, you get with x0. So you start from the end, you get an x0, which is now, in the end, a function. It's still random. It's simply a function of z0, right? Because you don't integrate z0 here. Okay, x0 is still random. It's a function only of the random variable z0, and of course of all the parameters. Okay. Not clear why one wants to do that, but here it's the important object. And then the Parisi functional for this zeta or this rho or this m or this k, which are the same thing. The Parisi functional, if you want, of this m and q, which is the same thing as the Parisi function of zeta, is simply given by, so here I have this x0, this guy, which of course depends on m and q through this integration, minus 1/2 of sum of mj theta prime of qj plus 1 minus theta prime of qj, where the function theta is simple. It's just theta of x, theta of q, is q nu prime of q minus nu of q. Okay, so theta is defined from the model, nu, and then you have this thing. Of course, this you could write also as the integral of, as an integral over zeta. Right, so this is just the integral of theta prime of q. This I could write as the integral of theta prime of q, zeta of q dq. All right, so anyway, that's the thing. So this part is quite simple. This one is not. Right? And with this, I have defined the Parisi functional for any discrete measure, any purely atomic measure. Right? And then I have my Parisi, the Parisi formula is now at least, you can understand what it says. And now you want, of course, to understand the inf of these things on all possible choices of m's and q's. This is a different type of problem. But before going there, let me describe maybe a more, it's not necessarily very useful. I want to describe a continuous extension to this, of this thing, of this Parisi functional to all probability measures, right? Here I define it as a discrete object. So here is this description, the continuous description. So it has been proven, so this function, Parisi function, can be extended to all probability measures, to the set of probability measures on 0, 1, and not only to atomic measures. Right? Or if you want, can be extended to from the set of step functions to all non-distribution functions. And again, as I said, it's not really very useful right now, but it's useful because that's the way that this description is the one that you find in the Mézard-Parisi Virasoro book of 87. And the first time I saw this equation, I thought, well, this guy's completely crazy. And in fact, that's the same description of this. So this is what I'm saying now is, oh, by the way, I should have said that. The theorem I mentioned here, the Parisi formula, so of course it goes back to Parisi. It has been proved in this context here by Talagrand, something like now 7 or no, 8 years ago, maybe more, maybe 9 or 10. And it has been proved for the case where you only have even terms, right? Where the p's, where it's a mixture of even p's. And it has recently, only last year, been proved in the full generality I gave here, that is even when you have odd p's, by Panchenko. And you know, it looks like nothing, but this 10 years was useful for that. In fact, the initial proof of this Parisi formula by Talleyrand was, in fact, came after a breakthrough, which was done by Guerra. And Guerra proved, in fact, such an equality is, of course, made of two bounds. Guerra proved one bound and introduced the natural interpolation scheme. And then Talleyrand finished it. So, and the proof of Talleyrand is really, the proof of the bound that was missing is really astonishing. I mean, it's really a tour de force. Maybe the nice part of the proof of Panchenko now, which extend to the odd case, is that in some sense it may have more, you may understand more what the structure of the argument is. Talleyrand was just a piece of brilliance, and this time you can follow the argument. I did read this thing a long time ago, but you don't get a very clear idea at this time how he did it. In fact, in the meantime, now you understand why he did this, but I think this approach by Panchenko is really very interesting. So in this paper by Guerra, he also explained what this Parisi functional is when you look at it on a set of all probability measures. So this is the set of probability measures. So here it is. So I will describe it just for p equal 2, but that is, you know, in the case p equal 2, remember nu of q is q square, so this thing is q times 2q, that's 2q square minus q square, so theta is also q square, okay? But, so p equal 2, remember, is just the Sherrington-Kirkpatrick model. But it would be valid for any p. All right, so look at the following thing. Look at the following equation. So you take a function f with variable q and y, and parameters, so he denotes them like this. You have parameters that okay, let me forget the parameters. Just take a function of q and y. Q will be seen as a time. Q will be between 0 and 1. And y here is a real variable, is a real number, and you should think of it as being the magnetic field. All right. So you look at such a function which satisfies the following equation. d over dq of f plus 1/2 of d second derivative in y of f plus zeta of, so I start with the probability distribution function zeta of q dyf square equals 0. You look at this PD. If you open Mézard, Parisi, Virasoro, you find this PD. And when you look at it and you are a probabilist, you're horrified. Right? You see, are you horrified? You know, even forget this thing. So of course it's a nonlinear PDE because you have this square here. That's not so much of a problem, but there's a much bigger problem, that you have a plus here. So it's not a parabolic equation, it's anti-parabolic. You know, I mean, it's a heat equation with a nonlinear term here, which goes the wrong way. So how can you expect anything reasonable from that? But, of course, the trick is that you want to solve this, but not with an initial condition in time, but with a final condition. So you want that f at time 1, so q here is between 0 and 1, and you want f that at time 1, if you want that overlap 1, on any y is given by log of cosine hyperbolic of beta y. The value of this function is not crucial. Of course, it's the same as this. So now you look at the structure of this equation. Now this equation is in fact not hard. Because of course what you think is, all right, if it's clear, if you want the final value and this thing goes the wrong direction, it simply means that you should invert the time, right? And look at this as a reverse time heat equation, and then it becomes a reasonable heat equation with a nonlinear term, right? And so there is a chance that you can solve that, and that this behaves well. This equation is, of course, a function of this function z here. This is the important parameter. But moreover, in fact, so initially you say, oh, terrible, because I have this nonlinear. So you must think of inverting the time to solve it. And this inversion of time, of course, is what is happening here. Here we are integrating backwards, right, from the final condition. But now, how do you deal with this nonlinearity? In fact, this nonlinearity is trivial. This is like a Hamilton-Jacobi equation. So let me explain how. So let's look at the case of this nonlinear PDE, which seems terrible. In the case where zeta is a step function, as over there. So in this case, you can integrate this completely. Right? So why? Let's take first, let's solve, but of course you have to start from the end. So let's look at zeta, let's look at an interval, say from Q, an interval AB simply, or let's say 0A time, where zeta is, let's assume that on an interval zeta is constant, equals a constant, say, little m. Okay? And assume that you have, or maybe this is not smart, let's start from 1 and here A. Right? So now this equation is simple. So you write dqf plus 1/2 of d of Laplacian, if you want, plus this m dyf square equals 0 on for q between, say, a and 1. And then you know the final value, f of 1. F at time 1 is given by some function, which is here log of hyperbolic cosine. And now you want to solve this. Right? So what do? You first invert. Let's look at, let's say, at f hat of, let's say, time t, which is now ny, which is simply obtained by saying f of 1 minus t and y. Right? I just invert the time. So now I'm looking at this equation with my time running, the time t running between 0 and 1 minus a. Okay? Simple. When I do that, what happens is I have the same equation here, except that this derivative takes a minus sign. The derivatives in y do not change. Okay? And so now I have a nice heat equation. Right? This is just natural heat equation, kind of, with this nonlinear term. And the difference is that now I have this value at time 0. So it's an initial problem for a heat equation type of things. Great. Then, of course, the next thing is, in fact, you want to get rid of the nonlinearity. So what you do is very simple. You just do the equivalent in this context of the Hopf-Kohl transformation. You consider f to be, let's say, so I have to be careful about who is the log and who is the yeah. Let me consider, let's say, a function g to be exponential, some constant, this f. All right? Simple. So what do I do now? I look at if I can write some form of equation for this G. Is that what I want, or is it the other way around? Yes, that should be what I want. So, okay, if I write dtg, not very hard, it's C dtf times G. Same thing for dyg. It's C dy f hat times G. And so second derivative of y, I do that for those who've never done this kind of computation. I have to differentiate that. I get C dy square f hat. And then I differentiate that again, which gives me a C square dy f hat square G. And this is the miracle. This is where you have the nonlinearity, exactly. All right, so now you see that if you take dtg, it's this times G, but this, in fact, is exactly that. Okay, let me put this C in factor here. Okay. If I just choose this C to be what I called over there M, so sorry, I should have, okay, let's take C equal M. Then this thing here is exactly this thing, right? dtf hat is this, right? So here, I just prove that dtg is exactly that. Maybe it was a 1 over C somewhere, which, no, because I have the same C here. Right? Simple. And the final value, the initial value is of just exponential C, this f hat at time 0, which is what we've been given over there, log CH of beta y. So I know the initial value. Now I'm down to solving a heat equation, right? Well, maybe I forgot some halves somewhere. Yeah, there was a half. There must have been a half. Yes, there was a half. So I have a half here. All right, so I'm solving the usual heat equation with an initial function. So I know how to solve that, right? So how do you, so I solve G, and then I know that this f hat is very simple. It's just 1 over C log G. Okay? So how do you solve for G? Well, this is the most trivial heat equation you can think of. So it's this G at time t and y is just the integral of the initial function, G0, which is this thing here, of y, times the heat kernel, I'm sorry, of z, zy, dz, or yz. All right? So you know this, but what is that? It's just, this is the, if you want another way to write it, is the expectation of G0 of, this is the density of a Gaussian variable with mean y and variance t. So you can write it as y plus square root t, let's say u, and this u is n01. Okay? All right, so we have our formula. We have the G, and we have the F. So now our F at time t and y will simply be, with my notation over there, 1 over m log of this guy. Right? Okay, and that's, and this guy, of course, here depends on, maybe this C was M. So. And now look, so now I know how to solve my F hat, so I know how to find my F. Because F is just F hat with time inverted. So it's 1 minus F T y is just this F hat of 1 minus T y, which you can then solve here. So if I solved this, I did this on one interval. right? The interval that went from A to 1, and now I've computed the solution down to A. Once I've done that, then I could go from an interval A to B. Again, I have the final value, and I do the same thing. And then recursively, I could go down to 0. Right? Look, that's exactly the structure that we have here. Okay, so I kept that on purpose. What do we do here? We start with something which is the log of CH of some Gaussian variable, whose covariance has been well chosen. Okay, so this log of CH is what I call G0 over there. And that's exactly what we have here. We have expectation of, so this guy is log CH. Oh, I forgot, I'm sorry. So an exponential is missing somewhere. F hat is, log, no, it's okay, that's it. No, the exponential is not missing. The G contains an exponential, right? So this is exponential, maybe I should write it like this. It's exponential m log CH of beta taken on this. Right? So it's exactly the same structure. And I integrate one variable, right? Because I just had one interval, one Gaussian variable. So it's exactly this. Look, 1 over m log expectation exponential m some log CH of Gaussian variables. Okay. So this iterative integration corresponds exactly to this integration of this PDE backwards when the zeta, the distribution function is stepwise. All right? But the nice part, so once you've realized this, and then you can go on and go down to 0. Once you've realized this, then you see that when you write it like this, you see that it should be possible to directly, I mean, first, it's possible to prove that this is defined even when this zeta is not stepwise. And then to prove, so when zeta is just a distribution function. And then to prove regularity of this, and the dependence of this f on this parameter zeta. And this is what Guerra does. It proves that this f, so what Guerra proves is that this f seen as a function of zeta, if you want, minus f for another zeta, okay, is bounded uniformly by a constant, which I think is beta squared times the integral, an L1 norm of zeta of q minus zeta of q dq. Okay, and this is pure PDE type of things. Once you have this, then you see that you can extend this function, this Parisi functional, to all distribution functions, this f at least. And and if you have an approximation of a distribution function by something stepwise, then this f will also converge, right? So this gives a meaning to this thing, which was purely discrete, now has been defined. And so the Parisi functional will be in this notation of Guerra. I didn't give it. The Parisi functional will be, okay, there's a log 2 for some parameter. I mean, that's not important, the constant. And then you take the function f, which is defined like this, at time 0, and the position y. So this is overlap 0, if you want, and this is the magnetic field. So if there is no magnetic field, you take f0, 0. And then you subtract this integral from 0 to 1 of q, zeta of q dq. This is specific to the case p equal 2, but here you would replace this by theta prime of zeta of q if you, I mean this guy, I'm sorry. Okay, let me write it in the general form. In the general form, that would be this. Okay. Which corresponds to, oh, okay, sorry, I just erased it, but in the general formula, you had exactly something like that. Okay? So this is the definition of the general the Parisi formula for a general zeta. And the important thing to remember is that it's a continuous extension of this thing on discrete objects. And this will play an important role. All right, so we have this very, very strange functional, and we have this theorem that says that the limit of the free energy is this. Now, so that's nice because we have this. So you can imagine that the proof of this is deep. You can't stumble on such a formula by chance. Now the next step, of course, of the question is, once you have such a variational formula, you would like to know things about it. So let's come back to the structure of let's forget this, the algebra of this, but let's look again at what the Parisi formula says. The Parisi formula says that the limit of the free energy, or at least its expectation, is this infimum of this Parisi function on all rho or zetas, whatever. So there are many things you want to ask. First, can we compute this? Right? So before that, is this infimum achieved somewhere? Is it a minimum? Right? So second, so if it's achieved, modulo some details, we will call such a measure where the minimum is achieved the Parisi measure. Okay? Second, is it achieved uniquely? Is there only one? Third, what is the meaning of, so imagine that you can see that. What is the structure of this rho? So in particular, is it purely atomic? Does it have in this case, we will say that there is a finite, it's a K replica symmetry breaking solution. And K here is the number of atoms minus 1. Okay? Is it, or does it has a continuous part? And then in general, we say that there is full replica symmetry breaking. F means full. RSB means replica symmetry breaking. But all that is good and well, but it's still is not the real question. The real question is, what is the meaning of rho? Right? What is this rho? Right? So rho, as you understand here, is seen as an order parameter. So rho is the order. Rho is the functional order parameter, as physicists say. Right? So as in the Curie-Weiss model, where you had the only parameter was the magnetization. Here, the only thing that seems to matter is this rho, which is infinite dimensional because it's a distribution on 0, 1. Of course, if it's purely atomic, it's not really infinite dimensional, but you don't know a priori what it is. So what does that mean? What is that supposed to mean? What is this object? So here's the interpretation of what it should be. And this emerged from the initial literature of Parisi, and in some sense we'll see that there is some truth to that. In good cases, it should be, so rho should be the asymptotic law distribution of the replica of the overlap of two replica under the Gibbs measure, sampled under the Gibbs measure. So let me explain what this is. So imagine that, so that's the interpretation of this strange rho. So imagine that you have, so you have the Gibbs measure, Gn, and so under Gn square, so you have your Gibbs measure, you take the product of the Gibbs measure by itself, which means you sample. So this is a measure on the cube square, right? So you sample, you pick, if you want, two replicas, sigma 1 and sigma 2. Okay, so you pick 1 point under the Gibbs measure and another point under the Gibbs measure completely independently. Right? And now you look at the law of their overlap, of what I call an Rn of sigma 1, sigma 2. If you want, it's also linked to the law of their distance. Here you're looking at the law of their inner product. Okay, and then this guy should converge in distribution to rho. Right, that's one, so that's what you expect. Of course, if this is not achieved, if you have more than one minima, all that, and even if you have one unique minimum, it's not clear that this would be true, but this is the way you should think about it. And we'll see that in some cases we can say it's true. So this means that this rho, this strange structure rho, which comes in the parameterization of the minima, is in fact the distribution of the angle, if you want, or the distance between 2 points taken at random. So why is that taken at random under the Gibbs measure? So why is that there? Why is this object ruling the whole game? That's not clear a priori, right? And what does it say? So let's imagine that, so that's the next thing. We have the free energy value. Of course, question 2 would be to understand the structure of the Gibbs measure. We will see that if we could understand well the structure of this variational problem here, we would understand well the Gibbs measure, in some representation that I will describe. And in fact, the recent proof by Panchenko, one can say that it uses much more the understanding of how to, together the understanding of the Gibbs measure and the free energy. So let's think of what this means. What do you expect for this rho? So that's important. Imagine that you are in a high temperature. So let's take first, what do you expect for this rho if it exists? Take first beta equals 0. Okay, no interaction. So what are you taking here? You're taking, or if you want, then you can expect that this extends to a high temperature region. So let me say close to 0, just for intuition. If beta is 0, the Gibbs measure is just a uniform measure on the cube, right? So if I take 2 points under the uniform measure on the cube, then what is the overlap? That's a question here for the youngest in the room. So you have, what is the uniform measure on the cube? You have an n collection of spins, which takes value plus or minus 1 with probability of half. All right? And now you are looking at the sum of sigma I times sigma prime I, where the two sigma and sigma primes are independent. It's clear that the law of large number applies. When you look at 1 over n sum of this thing, and it should converge to the mean of this. But the mean is 0. Right? So it's clear that the overlap should be 0. So in this case, this rho should be a Dirac mass at 0. Right? It should be purely atomic and have a Dirac mass at 0. That's what you expect. That's the signature of the high temperature, and this would be called the replica symmetry region. But now, let's go on the contrary to the region where beta is very large. So now you have a very large beta, very low temperature. Then what do you think could happen? You look at this, H. So let me draw a picture, which of course is impossible. I'm trying to draw a picture of the cube in n dimension, but that's not really easy. So imagine this is the cube, and I'm here drawing a picture of the, this picture is very misleading, but that's the only thing I can do. A picture of the function hn. This is a discrete object, of course. So I have this function hn, which might be something like this. Okay? So that's the energy value. Again, I apologize, but I cannot draw in n dimensions. So, and now your Gibbs measure, remember, is exponential minus beta hn. This is sigma, if you want, and this is hn of sigma. So of course, when beta is very large, the measure is supposed to be concentrated on some minimum. So if beta is large, if beta is infinite, really, it should be concentrated on the absolute minimum, which seems to be here. Right? But when beta is large, maybe it will be concentrated on all the minima below this. I don't know, somewhere here, maybe, I don't know, let me have a few, maybe a band like this. Right? That's what you would think. Now, if you take 2 points at random under this Gibbs measure, so the support of the Gibbs measure tends to be concentrated in parts of the cube where the energy is pretty low. And now, if you take 2 points at random, so the point you take under the Gibbs measure will tend to be either in this region or in that region, etc., or whatever, in this region of the cube. If you take 2 points at random, then typically two things could happen in this picture. Either the 2 points fall in the same region, or they fall in two different regions. If these regions are tight enough, then the overlap of 2 points falling in the same region will not be zero. Zero means that they are essentially orthogonal. Will be some value. That's the view that emerges from Parisi. But when they are, if these regions are far enough, then they might very well be orthogonal. So if you take 2 points from two different regions, then their overlap should be zero. Right? So in this scenario, the rho could be something like a Dirac mass at a point, a Dirac mass at zero with a certain mass, and a Dirac mass at some other point. This corresponds to the proportion of times where the two replica fall in two different pieces, orthogonal pieces. And this is the proportion of time where they fall in the same piece, and then this is all under the assumption that when they fall in the same piece, which they call lump here, then their overlap is essentially fixed. Okay, that is a one-step replica symmetry breaking thing, because we have two atoms. So that was a zero step, because we have one atom. This is a one-step replica symmetry breaking. Of course, you could imagine that you would have now a two-step replica symmetry breaking. So what would be a two-step replica symmetry breaking? It would be a situation where you would have valleys, again, so different valleys. That, if you have different valleys which are essentially orthogonal and in which the overlap is fixed, then you have one-step replica symmetry breaking. Now imagine that you have valleys, and inside those valleys you have a whole lot of smaller valleys, deeper valleys. Right? Then in order to compute the overlap, you have to do the reasoning I was doing before twice. When you take two replica, they might fall in two completely different big valleys, and then their overlap should be zero. Or they might fall in one big valley, and then in this big valley they could fall in the same sub-valley, where then you would have one value for the overlap, or in two different sub-valleys where you would have another value for the overlap. So then you would have three values for the overlap. Okay? What I'm describing here is what is called an ultrametric structure. It's a tree. What I'm saying basically here is that at low temperature, what one expects that the support of, if this picture is to be valid, the support of the Gibbs measure has essentially the structure of a tree. That is, you have regions and regions inside regions and regions inside regions, etc. And this is a structure of a tree, which is usually called ultrametric. So this thing, when you make it much more formal than what I'm saying here, is the real holy grail of this of the theory, is to understand this ultrametricity conjecture of Parisi. The conjecture, which I will make much more precise, says, in good cases at least, the Gibbs measure, the limiting object here, the Gibbs measure behaves in an ultrametric way. There is some kind of a tree structure behind it. Now you have to be a little careful, because I described what a tree with, one level would be, two levels. You could go to 3 levels. You could have valleys, inside valleys, etc. But what would correspond to the case where rho is continuous, has a continuous part, when it's not discrete? Right? You need some notion of a continuous tree there, which is way more complicated. Right? So we'll come back to that. That's the subject of the talk, of the course, at least for the equilibrium part. I will try to describe a little bit of what is known there. The second part of the talk will be about dynamics. How do you move in this landscape, if once you have the picture that the landscape is like this? So you can imagine that if you have this very complicated valleys inside valleys, when you look at the way you move a Markov process that would have this measure as an equilibrium moves in this landscape, will have many, many different time scales. The time it takes to escape from one type of valley to get in another type of valley, etc. So there's a whole range of time scales in which things could happen. And what I will try to explain for the dynamics is what we know about at least a part of the range of those time scales, and how a part of this is very, very universal. Okay? Now, what is expected from all this? Because I'm saying, so what is known first? Very little is known here. The structure of this variational problem is still very, very open. And that's really a mess. But a few things are known, and I will tell you some very good cases where we know things there. But what is expected by the physicists is the following. If you take the Sherrington-Kirkpatrick model, then let's say with no magnetic field, you should go from a region of high temperature, then there is a critical value of the temperature, below which you would have full replica symmetry breaking. Full. That is, this rho has a continuous part, which means strange object. What is also expected is that if you take a p-spin model, when p is larger than 3, the structure is different. 2 and 3 are very different. If you take p larger than 3, you're supposed to go, you have a high temperature region, then when temperature goes lower, you would get to a region in temperature, and this is proved in part by Talleyrand himself, where you have one-step replica symmetry breaking, so this decomposition of the support in lumps. And then if you go even lower in temperature, you're supposed to have full replica symmetry breaking. Okay? So these results go back to the physics, to Gardner in the 80s, and to my knowledge are not confirmed completely, but that's what is expected. For mixtures, I don't really know what is really known, in fact, and a lot of things can happen. I can show you examples. All right, so that was just overview of what the result is and what the problems are. Now maybe a pause of 3 minutes, and then I will explain the same formula for the spherical case. For the spherical case, there is a miracle. I mean, it's that this formula, which has a priori the same structure, in the end, the formula can be simplified much more. The Parisi formula can be Parisi functional can be written in a much simpler way, and this is due to Crescenti and Summers, and was proved by Talleyrand. And there you have a much neater expression of the Parisi functional, and because this is neat, some of these questions are answered positively. All right, and I will tell you what's happening in the spherical case. All right, after the break. So Manuel asked me a question which prompts me to correct what I wrote here, I mean to make it more precise. When I say the law of the overlap should converge, there's a question mark, of course, here, to this rho. Of course, I meant the law under this distribution, so I should write this law under this distribution, expectation of Gn square. Right, that is, you take first two replica for fixed disorder. For the same disorder, you take two replica, and then you take the average on the disorder. Okay. All right, so now let's go for the same question, for the same model, but on the sphere. Spherical mean field model, spherical case. All right, so remember we have the same function. So sigma n now is the sphere of radius square root of n. And we have the same function. The h is exactly the same. Is identical as before. Right? So remember now we have the same structure of covariance, except we're looking at this on the sphere rather than on the vertices of the cube, which are on the same sphere. Right? So, and we ask the same question. The theorem is now of the same nature, so the Parisi formula is also correct. And the formulation I will give is due to Crescenti and Summers. The proof is due to Talagrand in a special context and to, is it Chen or Penchenko and Chen? I forgot in the general context. Just Chen, yes, Chen. So, and this is very, very recent. It's still a preprint, I think. So the Parisi formula is of the same nature. Limit of 1 over n log. Oh, I'm sorry. Expectation of log of Zn is the infimum of some Parisi functional of rho, where rho is a probability measure. I just have to describe what the Parisi functional is. And here, we could have an expression of the same nature, but as I said, there's a much easier thing. So the Parisi functional of a distribution, let's say I say rho, or I could say zeta. Zeta here is the distribution function, is written like this. So I define first zeta hat of q for any distribution function zeta to be the integral from q to 1 of zeta of s ds. Okay, that's just a definition. And now I assume that the support of the measure defined by zeta does not touch 1. It's on the left of 1, strictly. So I assume that there exists a q hat such that zeta of q hat is 1, and this q hat is strictly smaller than 1. Right? So this means, so zeta defines a probability distribution in the interval 0, 1. This tells you that, in fact, the support ends at q hat. All right? So assume that. Now, in this case, the Parisi functional of zeta is 1/2 of integral from 0 to 1 of zeta of q, nu prime of q dq, where nu is our usual function, which defines the model, plus h square, if there is a magnetic field, zeta hat of 0, the integral from 0 to 1 of zeta, plus the integral from 0 to q hat of dq over zeta hat of q. So why is it useful here that q hat doesn't touch 1? Zeta hat of q, of course, is 0 when q goes to 0 when q goes to 1. So this thing would be a problem when you're close to 1. Plus log of 1 minus q hat. Okay, so let's look at this functional. It's way simpler than the one we had before. Right? This looks like a simple functional compared to what we had before. You don't need to solve a PDE or integrate a bunch of random variables. It's just there. So you have a bunch of integrals involving zeta, zeta hat, and the function nu, which of course plays the role of the model here and the magnetic field here. So a priori, this thing could depend on the q hat, right? Because you may choose different q hats. It's easy to check that this does not depend on q hat, right? So you could choose q hat, for instance, to be really the top point of the support of zeta, right, of the measure. Okay, so that's defined when there is such a q hat, and if there is no such q hat, you define the Parisi otherwise. You define this Parisi functional to be infinite, to be what? I want it not to count, so probably, yeah, I don't define it, that's better. Now, so, okay, I could have written Parisi of zeta here, and then you could take the infimum on things where the support is strictly smaller than 1. All right. So this formula for the Parisi function in the spherical case is due to Crescenti and Summers. As I said, in the 90s, the proof is due, of course, to Talagrand, and more recently, Chen. Okay. And again, this proof now, this result is now valid for any mixture. All right. So in this case, so we have the same question now. In this case, can we say something about the structure of this variational problem? And in fact, we can say, in the spherical case, we can say a bit more. So that's a theorem, which is also, so I didn't check that Chen extended this, but I'm sure it's true. It was proven in the case of, in the first paper of Talagrand. So first, so I can answer the first two questions. The infimum is achieved. And second, uniquely. So there exists a unique minimum. So this minimum we will call the Parisi measure. Here there is a Parisi measure, right? Whereas here we are not sure in general. And third, under a certain condition that I will mention quickly, the distribution of the overlap of two replica under the measure, take the Gibbs measure square, and then you take the mean, converges to the minimum, to rho, where the minimum is achieved. So this Parisi measure is indeed, in this case, unique, well-defined, and is the limit of the overlap. Right? So the interpretation is correct. What we haven't yet answered is this. what is the structure of rho, right? We answered question 1, 2, this thing over there, but not the structure of rho. In this case, so in particular, do we have something which is one-step replica symmetry breaking or full or? All right, so the structure of rho, what Talagon proves is if the magnetic field is non-zero, that's why I included it there, and if, I'm sorry, this was here. I had the room for that. This is proved when H is non-zero, and so that's and beta P is non-zero for OP. We will see that this condition is not necessary, but that's what Talagon proves. So it's a bit limited now, but we'll see why this happens. Then the distribution of the overlap converges to this. All right, so now what about the structure of rho? So what Talagon could prove that if the function nu second to the power negative 1/2 is convex, which is like a strange condition, then the cardinal of the support of this rho is less than 2. So this means under this strange condition, then it means that you have at most one-step replica symmetry breaking. Right? You can have two atoms. This is what this tells you. Rho is atomic, and you have either one or two atoms. One atom means replica symmetry. Two atoms means one-step replica symmetry breaking. Right? So that's a simple situation. Example of that, if you take nu of R to be R to the 2p. Right? That is a pure 2p spin. If you take a pure p spin model when p is even, then this is true. Right? So now I think this also has been extended to the odd case. Right, Tuka? Yeah. That was the initial statement by Talagon, and now this has been extended. So what this tells you is the following. If you take a pure p spin, in the spherical case, then it is one-step replica symmetry breaking. Okay? Depending on the temperature, right? At high temperature, it will be replica symmetric. At low temperature, it will be one-step replica symmetry breaking, which is the picture I just explained. On the sphere, you will have regions which are essentially chosen at random, which means they are essentially orthogonal. And inside those regions, and the mass of the Gibbs measure will be essentially concentrated on those different regions, where inside this region, when you take 2 points, the overlap is fixed. All right? But that's for the pure case. It's absolutely not true that it's always one-step replica symmetric for the spherical case. And there are many, many cases where, in fact, the answer is full. That is, this rho has a continuous part. So here's an example that Talagon gives. Take the function nu of q to be beta square hyperbolic cosine of a times q minus 1, where a is a positive number here. Easy to check that this is, so let's forget, the beta square is just, to check that this function here, I don't need the beta square, is of the type that we have over there. If you expand it in power series, the coefficients will be non-negative, right? So we have, this is a spin glass model function. And what he proves is that, in fact, in this case, so it's easy to compute in this case, he can say something about the limiting object. And in particular, he says that the support of the rho in this case is an interval, say 0, Q0, That rho has a continuous part there. And on top of that, that rho of the singleton Q0 is 0. It may have, there is no atom at the top thing, which is, well, as we will see, which is important. In all the hard spin cases, at least in the physics intuition, there is always an atom at the edge of the support. Right? That's what they think. In the spherical case, Talleyrand was the first probably to notice that it doesn't necessarily happen. This condition of giving zero mass or positive mass at the top of the support, we will see, is important. Okay, so in this case, you have full replica symmetry breaking. So this spin glass is much more complicated than this spin glass. Oh, I'm sorry, this becomes Q, it was R. All right. So everything can happen. And, but at least we know that there is a unique minimum, and that, at least in good condition, it is really the distribution of the overlap, the asymptotic distribution of the overlap. And we know this fact here, which is important, that is, for pure p-spins in the spherical case are indeed one-step replica symmetry breaking. I just told you before the break that if you take pure p-spins in the Ising case, then there is a region where they are supposed to be one-step replica symmetry breaking, and then the region of lower temperature where it's supposed to be full. So these two transitions for the pure p-spins are supposed to be true on the on the Ising case, but are not true on the spherical case. So the spherical case, in this respect, is simpler. And if you read the introduction of Talleyrand's paper on this, he explained that, yeah, the wisdom in physics was that the spherical case should be simpler, probably because of what I said. They expected that the end result is simpler. If you have one-step replica symmetry breaking, it's simpler than full. But in fact, the proof of this is even harder than the proof of the Ising case. So all these results are really a little formidable. All right, so now I've told you what we know about the spherical and hard case. In fact, the next step would be now to understand what happens in the for the Ruelle cascade or the Poisson-Dirichlet cascades, which are the limit of the Grem. So I should introduce now the Rem model and the Grem model, but I don't want to put too many models, so we'll do that next time. I want first to explain now something which, in fact, I believe is really beautiful, and which explains why so I don't know to whom this should be attributed. Probably the first introduction of that should be attributed to Eisenman and Arguin. But then the expansion is probably due to Talleyrand, Panchenko himself a lot. And this is really a beautiful view of this, which is purely geometric now. Forget physics and all that. This now will be really abstract and geometric, and I believe I'm not the first. I'm impressed by what I've read here while preparing this class. And even though things are not very completely clear at this point, I wouldn't say that it's clear that everything works, but the structure is really convincing. I think that's really the object that should be studied. So here is now a little bit of abstract things which will shed light on this very strange thing. So I want to introduce what are called asymptotic Gibbs measures by Panchenko, and in this context, and probably called ROST, where at least a few years back, I think it's the same object that was called ROST. ROST meaning random overlap structures. Okay, so here's what the story is about. So let's start with GN. Okay, so our GN, that's the Gibbs measure. It's a measure on the, let's say for the moment I'm talking only about the Ising case. So this is a measure, it's a random measure, of course, probability measure on the cube here. Right? which is included in, I will change the notation here, in the sphere of radius square root of n. The cube is, of course, inside the sphere of radius square root of n. So it's a random measure, and we want to understand this random measure in the limit when n goes to infinity. That's what this whole thing is about. The question is, how do you do that? Right? Again, we are in a mean field context. How do you define a limiting object for Gibbs measure on a space which changes with n? Right? So again, for those of you who have done some easing model or some statistical mechanics on the lattice, it's a different situation, because over there, your finite graph would be a box in the lattice, and you let the box go to infinity, you know all these boxes are in the same space. So at least you have an idea of what a Gibbs measure could be. It's some sort of measure on the configuration space in infinite volume. Of course, you have to be very prudent with that, but you know what the object should be. Here, what do? What is the limiting object when you let n go to infinity? This is a measure on this. What can you do? Right? This object becomes, has no limit, in fact, or same thing for the spherical case. What is this infinite dimensional sphere? So one way out of that, which is the way I thought for a long time about mean field models, not necessarily disordered, it's the propagation of chaos view. That is, what you do is you take a block, you project this on, say, k coordinates. You look at the distribution of, let's say, the first k spins. You fix k equals 17, and then you let n go to infinity. This gives you a distribution, and then you may try to understand what those finite dimensional marginals are. But you see that you lose a lot of information because you are just looking at, 2, 3, 4, 17, but an n is very large. So typically when you do that for the models we have here, in the high temperature regime, what you expect is that these guys, when you fix k spins, then they will be essentially, the distribution of that will essentially be uniform at high temperature and not at all uniform in low temperature. But you lose a lot of information. So there must be another way to go to the limit. The other way is to construct the right object, which will be immediately on a space in which you can go to the limit. And the right object is the following. So the first remark is this. The distribution, if you take now, and you know that you are right on target when people begin to talk about symmetries. There are two important symmetries in this measure. The first one is if you do a permutation of the indices, right? Then clearly you get the same distribution. Right? If you permute the indices of the sigma i's, that is, you do a permutation of the directions here in this n-dimensional space, you get the same distribution. But permutation are just, in fact, here isometries of the cube. That's what we're looking at. But now what happens if you take an isometry of the ambient space of the sphere? So if you take U to be an orthogonal transformation, right? And now you take Hn of U of sigma. Right? So you take your spin configuration, which is on this vertices of the cube, and you rotate it. So now when you've rotated it, this thing is not necessarily back on the cube. But this object is well defined. In fact, it's the same thing that we define on the sphere. The distribution of that is the same as the initial distribution. Right? Why? You can try a direct computation, but you can simply remember that the covariance of this was a function of the distance only. So the covariance of that is a function of the distance, but the distance has not been changed by an orthogonal transformation. So the covariance is the same. So you have two Gaussian processes centered with the same covariance, the same distribution. Right? So this tells you that, so of course the distribution of Gn now, if you take the Gn and you take its image by an orthogonal transformation, a rotation, then this, as a measure, has the same distribution as Gn. Right? Except, of course, not really, because this is not really true. Because this is supported by the vertices of the cube. This is supported by the vertices of a rotated cube. Right? So this is not exactly true. But what is true here is that if you take the distribution now, that's the important thing. If you take the distribution, you take a k-tuple of points, and you look of replica, and you look at the distribution of their distances or their overlaps. Right? This will be invariant by any rotation. Right? The points themselves are no longer on the cube. They may be on a rotated cube, but the distances between them are the same. So that's the idea. What you do is you consider a sequence of replica yeah, in the English tradition, I guess you should say replicas. And let's say sigma 1, sigma L, when L is larger than 1, which are sampled under G infinity. Okay, so you have your Gibbs measure on the vertices of the cube, and you take an infinite sequence of replica. You choose an IID sequence of points according to this Gibbs measure. And now, once you've done that, you look at the following. You define the infinite matrix or array of overlaps of these replica. So the matrix, which will be defined by R, maybe an N here to remember that it's a finite dimensional object. And this matrix R of L prime is defined to be the overlap of sigma L, the overlap of sigma L prime. Okay? So now you have this collection of points on the vertices of the hypercube, and you look at their distances, if you want, or their overlaps. This creates a large matrix. This, of course, is just a Gram matrix. Right? Remember what a Gram matrix is. If you take points, if you take a number of points, you look at the symmetric matrix, which is simply the matrix of their inner products. This is a Gram matrix. So we're just taking this Gram matrix, which is random, because it depends on in fact, it's doubly random. There is the randomness on the Gibbs measure, and then under the Gibbs measure, you sample these guys, and you have this thing. So this infinite matrix, in fact, encodes all the distances between all the possible pairs, not only one. That's very different from what we're obtaining over there. What the Parisi formula says is that the order parameter is the distribution of one overlap. So it says something like, once you understand the distribution of one overlap, you get everything. Here I'm keeping much, much more information. Right? I take this infinite sequence of replica and look at all their possible distances or overlaps. This is one large matrix. So why is that interesting? This thing here now, because of what I said here, which was not exactly true, this thing now is insensitive to the position of these sigmas. If I rotate my sigmas, I don't change this thing. So it just encodes the distances between the sigmas, but not their absolute position. Right? So the distribution of this, if I do an orthogonal transformation, the distribution of this will be unchanged, right? But now, this object, I could look at it as, so it's this big Rn. I could look at it as an element. Of course, it's an infinite array. So there, of course, there's a question of topology. What kind of topology do I choose on these arrays? I will choose following Panchenko here, I will choose just the simplest one. That is, I see this as a product from, so maybe before going to topology, a little algebra. This thing has the following properties. Is such that, first, of course, it's symmetric, right, obviously, and it's non-negative definite. By that I mean what? I mean, let's say you take, so this is an infinite matrix, let's say you truncate it at size m, which means you take m replica, then you have an m by m matrix, which is obviously symmetric and non-negative definite because it's a gram matrix. Every time you take a gram matrix, it's non-negative definite. But second, it has also another property. It's weakly exchangeable. That's the crucial property. So what does that mean? That means if you take any permutation with of the integers with a finite support, you take let's say a permutation of the first m integers. If you permute that, then the permuted indices, the distribution of R will not be changed, right? The distribution of, so if let's say a pi, because I can't call it sigma, is a permutation of n with finite support, so it only changes, then the distribution of this Rn of pi L prime, the whole thing is the same distribution as the Rn and L prime. Right? So I have this weakly exchangeable, let's forget weakly, this exchangeable array of matrices which are, or this array which are symmetric, non-negative definite. Note that the two conditions here, 1 and 2, in fact only depend on the finite dimensional distribution of this infinite thing. Right? I have this object. Now, the nice thing is that these objects are all in one space, right? The space of infinite arrays, right? So all these Rn, I could see them in the space of product for L prime, maybe L smaller than L prime, if I want to have the symmetry of R, right? That's my way of defining the array. This space here, I can endow it with the convergence, pointwise convergence and finite marginals, because everything here is finite marginals defined. I have a certain space here, let me call it M. This is the space of all these arrays. And in fact, this guy lives in a small part of this. It lives in the space of such arrays that are symmetric, non-negative definite, and exchangeable. All right? Now this space is fixed, doesn't depend on n. And so if we could prove that this Rn converges to something, and distribution, so this space I endow with the natural topology I just mentioned, and then I have a Borel space and a Borel structure. So Rn in fact defines, the law of Rn is a probability measure on this. So if the law of Rn converged to the law of something, if this, right, then we'd be happy this limiting object should contain a lot of information. Right? This limiting object would, of course, R inherits, R is a random thing because it's a distribution, but inherits the properties 1 and 2. right? Because these properties were only on the finite dimensional marginal, and that's what I'm looking at, right? So this limiting guy, or this limiting law, will also be supported by symmetric, non-negative, definite, and exchangeable things. So, but why would that converge? There's a very good reason for that. Is that compactness is trivial here, or tightness if you want. It's for free. Right? Because remember that the overlaps are all between -1 and 1. So they are bounded. So the space in which, so it has property 1, 2, but also, in fact, it's in, I could put here -1, 1 instead of R. So this is a compact space. The Rn live in a compact space. A product of compact space is compact, right? So there is no question of tightness, right? So the distribution of Rn on this big space is tight. So the only thing we have to understand now is there. So we could look at all the limit points. So this is now reminiscent of what you do for Gibbs measures, right? You have on ZD. You prove some form of tightness, and then you say, I look at all the possible limit points. And you're happy, you have no phase transition. Everything is good when you have only one limit point. But maybe you can have many. So the question now is to understand all those limit points. So what are those limit points? They are distributions on the space here, of course carried by -1, 1 to the product of -1, 1. Which have those two properties, 1 and 2, right? So is that enough to characterize them? Of course not, because here, these properties do not depend even on my model. So somewhere the model should be, I need something, right? So where should the model be? So first, before we go there, but at least we have here a strategy of having a limiting object. And we will see that there is an enormous structure in these guys. So before we go there, do we lose something when we encode the Gibbs measure by this? Because that's an encoding of the Gibbs measure, right? And then we can pass to the limit. But maybe we've lost something when we do this. So did we lose something? Of course, when we did that, we lost the location of the hypercube, really. But because here you just have the overlaps, you don't have the points. But this contains, I'm claiming that this contains the whole information, this encodes the whole information on the Gibbs measure up to orthogonal transformations. If you know this, at this finite level here, you know the Gibbs measure, in fact. Why? So let's forget this abstract thing. We have this collection of replica, of overlaps or distances between the points. It's an infinite collection now. So let's look at the following. In fact, on the cube, you have only 2 to the n points. So if I take an infinite collection of points, I will have repetitions. I can group them in blocks, right? So how do I do that? How do I recognize, by just looking at this matrix, not knowing where the points are, that in fact L and L prime corresponds to 2 replica that were the same? It's trivial. If sigma L is sigma L prime, the overlap is 1. So every time that in this matrix, which is a matrix of numbers between -1 and 1, every time you see a 1, it means that, so of course on the diagonal you have 1s, but every time you see a 1 outside the diagonal, it means that at L and L prime, the 2 replica were the same. So you group them. You group all these different things by, as soon as you see a 1, you make one package of them. And you have at most, and you have in fact 2 to the n such things, right? But now, once you have these objects and you let m now, the size of the number of replica grow to infinity, right? N is fixed now. Then the law of large number tells you that you can recover the Gibbs weight of this sigma L. of it. Take 1 point, sigma 0, 1 point on the cube. Say the one made, then here you have a large number of repetition of this thing, all the guys where you have a 1 with them. And obviously now, by the law of large number, by counting this, how many you have, what's the proportion of them that you have if you have m replica, the law of large number tells you that this will converge when m goes to infinity to the Gibbs weight. Right? You had a measure, you sample it, and then of course, then you get the Gibbs point. But maybe you can have many. So the question now is to understand all those limit points. So what are those limit points? They are distributions on the space here, of course carried by minus 1, 1 to the product of minus 1, 1, which have those two properties, 1 and 2. Right? So is that enough to characterize them? Of course not, because here, these properties do not depend even on my model. So somewhere the model should be, I need something. Right? So where should the model be? So first, before we go there, but at least we have here a strategy of having a limiting object. And we will see that there is an enormous structure in these guys. So before we go there, do we lose something when we encode the Gibbs measure by this? Because that's an encoding of the Gibbs measure. Right? And then we can pass to the limit. But maybe we've lost something when we do this. So did we lose something? Of course, when we did that, we lost the location of the hypercube, really. But because here you just have the overlaps, you don't have the points. But this contains, I'm claiming that this contains the whole information, this encodes the whole information on the Gibbs measure up to orthogonal transformations. If you know this, at this finite level here, you know the Gibbs measure, in fact. Why? So let's forget this abstract thing. We have this collection of replicas, of overlaps or distances between the points. It's an infinite collection now. So let's look at the following. In fact, on the cube, you have only 2 to the n points. So if I take an infinite collection of points, I will have repetitions. I can group them in blocks. Right? So how do I do that? How do I recognize, by just looking at this matrix, not knowing where the points are, that in fact L and L prime corresponds to 2 replicas that were the same? It's trivial. If sigma L is sigma L prime, the overlap is 1. So every time that in this matrix, which is a matrix of numbers between -1 and 1, every time you see a 1, it means that, so of course on the diagonal you have 1s, but every time you see a 1 outside the diagonal, it means that at L and L prime, the 2 replicas were the same. So you group them. You group all these different things by, as soon as you see a 1, you make one package of them. And you have at most, and you have in fact 2 to the n such things. Right? But now, once you have these objects and you let m now, the size of the number of replica grow to infinity, right? N is fixed now. Then the law of large number tells you that you can recover the Gibbs weight of this sigma L. Take 1 point, sigma 0, 1 point on the cube. Say the one made, then here you have a large number of repetition of this thing, all the guys where you have a 1 with them. And obviously now, by the law of large number, by counting this, how many you have, what's the proportion of them that you have if you have m replica, the law of large number tells you that this will converge when m goes to infinity to the Gibbs weight. Right? You had a measure, you sample it, and then of course, then you get the Gibbs weight. So if you have this infinite matrix, then encoded in it, it's not a simple thing because you have to take a limit, you have the Gibbs weights. So we have the whole Gibbs measure there. Except for one thing, you cannot know from there where the points are. Right? You cannot know if your point is here or there in the cube. And it's natural. In fact, you know the whole Gibbs measure up to an orthogonal transformation. Right? So in particular, swapping the vertices or moving the cube, you can't feel. But this information is in fact irrelevant for everything we do. Again, because the covariance structure only depends on the overlap, and everything we've seen later seems to also only depend on the overlap. So this matrix encodes completely the Gibbs measure up to orthogonal transformations. So we haven't lost anything serious doing this. Right? So if we happen to be able to prove that there is a convergence, for instance, because there's a unique limit point here, then this guy has inherited, in a complicated way, of course, all the structure that there is in a Gibbs measure. Okay? So these limiting objects here, that's what Panchenko calls the asymptotic Gibbs measure, and equivalent to what used to be called ROS, the random overlap structures. But now, so the question is the following. When I say that, somewhere in this row, the model, that is the function nu, should be encoded. Otherwise, in this R, I mean. So where is it? Now imagine that I have G, the distribution of rho, of the limiting object here. Okay, I don't need to introduce that. Imagine that I have this R, which is this limiting random object. All right? So this is a distribution of an infinite array, which has all these properties. What was the order parameter was the distribution of one element, right? What we call the order, the functional order parameter, that was, remember, rho, the Parisi measure, was the asymptotic, was supposed to be the asymptotic distribution of the overlap of two replica. Sample under the Gibbs measure, right? So what is that supposed to be? This is in fact supposed to be the distribution, asymptotic is already taken here, the distribution of R12. Right? You take your huge array, then you can look at the distribution of one element, right? And that's what we call rho. So here there is something else, which is, and of course they're all the same. The distribution of R12 and R27 is the same. But a priori in R you have much, much more information because you have the joint distribution of R12, R23, R35. R12 is like the distance of 2 points. Right? But a priori in R you have much more. You have if you take 3 points, you have the distribution of the distances in a triangle. Right? So it's not clear that knowing the distribution of 2 points, of the distance of 2 points, is enough. Right? So the question here is, why would, and in this distribution, the model nu was encoded. Remember? Because this thing was the minimizer of the Parisi function, in which, of course, the model nu was. So why would the distribution of R be determined by the distribution of one element? And one non-diagonal element, of course. Okay? That's a serious question. The question is, and it's clear that it cannot be simply by these two things. The question is now, if you have this abstract object, the limit law on these guys, what kind of conditions will impose that once you know one element, one distribution, it's a very specific thing. It cannot be true for any random measure. You could start from any random measure on the sphere over there and do this construction. But then something must be specific, and that's the intuition of Parisi, to the spin glass situation where if you know the distribution of one element of this infinite matrix, you know everything. So for that, you need some constraints, very hard constraints. So you need to identify some very strong constraints on the model. So the constraints we will identify will be on Rn, the finite thing, and thus on R. So these constraints are now known, and that's called the Ghirlanda-Guerra or the extended Ghirlanda-Guerra identities. This plays a very big role. I'll talk about that. They have been discovered by Ghirlanda and Guerra. Here's Guerra again. So I'll say what that means. It can be entirely expressed in terms of this abstract setting, not necessarily on the, you could start here. Forget the spin glass measure. I have a sequence of random measures in the sphere, and then I start this thing. Right? And then you would not have the Ghirlanda-Guerra constraints. But because the models come from our spin glass model, we will have these constraints that we'll describe. And these constraints we will see impose some structure on the limiting object, and essentially they impose this. That is, when you know one distribution, you know the whole distribution. Right? And this then would explain why this is the order parameter. So in particular, if you can prove that there is a unique Parisi measure, then you would prove also that there is a unique limiting distribution for this guy, and so you would prove convergence here, because we have tightness. Okay, and so I think I should stop. But this is what the strategy is to explain a little more of this, and then for that we will see next time there is a very beautiful. I never trusted these things to be very important in probability, and I'm stunned that they are. There's a beautiful representation theorem of these possible limits here, which builds only on the fact that it's symmetric and exchangeable, only on these two properties. The important part being the exchangeability. Symmetric and all that is kind of an add-on. When you have an infinite array of an exchangeable infinite arrays, then you have a definity type. So this is usually called a Gram definity matrix because it's exchangeable. And as you know, definity has proved has studied this. So there is a definity type result which describes all the possible limits of exchangeable, all the infinite exchangeable arrays distribution. Right? So this definity thing definity did it for not for arrays but for sequences. So this thing for arrays has been done by Aldous and Hoover, and then reproved and specialized in this case by Dovbich and Sudakov, and then proved again by Talagrand and maybe by Penchenko first. So there is a general representation of definity type, which says that the law of these guys are necessarily mixtures of IIDs. Right? The definity theorem, if you don't remember, I'll recall that, but the very, very probability 101 theorem by definity is if you have an exchangeable thing, then it will be a mixture of IID. We'll have something of the same nature here, and this Dovbich-Sudakov theorem gives a structure. It's a representation theorem which gives a very nice structure, and we'll understand what that is. Okay? So again, if you think of this as on ZD like Gibbs measures, you have tightness, then you have to describe what the things are, and then you have extremal element, you have mixtures. It will be something of the same flavor that we have here. All right, so I'll try to describe that tomorrow.